This is a histogram of the number of measurements taken at any given measured value. And this is for data that has a normal distribution. It means that if you take a data point, it might lie at this measured value. You take another data point, it might lie here, and one might lie here. But what you would find is if you took repeated readings over and over and over again, that most of them would be clustered in the middle, and you would have fewer as you went further away from the mean value, which for a normal distribution would be right in the center. It's possible that you might have one or two at the very extreme values all the way out there. And for the purposes of our Year 11 analysis of data, we're going to call this distance here between the most extreme value on each side. That whole distance there is called the range. And we'll often refer to the half range, which is obviously just that length of one of those from the center out to the extreme value. What we're going to talk about in this video are two ways to quantify the uncertainty. One is the uncertainty on a single measurement. And what is the uncertainty for the average value of a whole bunch of repeated readings? Working out the uncertainty for an individual measurement is actually pretty straightforward. We just need to say, given any individual measurement that we take, how far from the average value is it likely to be? So if we took a measurement, we would know that that measurement would be within that half range from the average value. We can only estimate that uncertainty for the individual measurement after we've taken a whole bunch of data to see what that distribution looks like. How certain we are or uncertain we are about the average value depends on how many measurements we've taken. If we've only taken a couple of readings down here and took an average, it might be that our average was a little bit further this way or a little bit further this way. It's actually really hard to tell if you've only got, say, 2 or 3 measurements. The more measurements you take, you actually see this pattern starting to build up, which gives us this nice curve here. So the more measurements you take, the more tightly constrained this average value is. And we'll see how we can quantify that, put a number on that. If we take repeated readings, how we can give a number to the uncertainty of that average. Here is an example. I have 5 trials or repeated readings of measuring the voltage across a power supply. Now, you'll learn more about that when we get to the electricity unit, but you've probably come across something like it at high school. I am not going to go through the maths because I'm sure you can do it to work out the average value of these 5 readings, and it's 1.56 volts. Now, just keep in mind that this statistical analysis that we're doing here is not particularly sophisticated, but it will do for the level of the stuff that we're looking at in this course. So to work out the uncertainty on a single measurement, any single measurement is likely to be within half the range of the average value. So that's actually a pretty simple calculation. So an uncertainty of an individual reading is just half the range. So the range is the maximum minus the minimum. Okay, so any existing or future measurement is likely to be within half the range of whatever your average value is. So we say that an individual measurement or reading has an uncertainty of half the range. Now, it's really important to point out here that the value of this uncertainty here is not necessarily the same as whatever your instrumental uncertainty is, so whatever uncertainty you anticipated based on the size of the divisions on your measuring instrument. The uncertainty that you calculate for an individual reading might turn out to be larger than the instrument uncertainty because of sources of random error that cause the numbers to vary evenly above and below where your average value is. So if you go back and look at our data here, the range of the data is the maximum value, which is 1.59, minus the minimum value, which is 1.53, which gives us a range of 0.59 0.06 volts. And so our uncertainty on our voltage, which we symbolize with that triangle there, the uncertainty, is half the range, which equals 0.03 volts. So we can say that on any individual reading that we have listed below there, 0.303 volts is the uncertainty on the number listed. Now this number of uncertainty supersedes any uncertainty estimate that you may have made based on the size of the divisions on your measuring instrument. Now we want to look at the uncertainty of the average value of all that data combined. Now, as we said before, if you take lots of readings, you are going to know that average value better and better the more readings you take. And so the calculation for the uncertainty of the average value is going to reflect that the more readings you take, the better you know that value, or the smaller the uncertainty will be. So the uncertainty of the average value starts off again with the half range, because obviously it depends on how scattered that data is, but we're going to divide it by the square root of the number of measurements that we took, or the number of readings we took. So in our example here, we would have 1/2 of the range, which is 0.06, divided by the square root of 5 readings that we took, and that gives us, if I've done my calculations right, 0.0134 volts. Now remember, this is an uncertainty, and we really can't specify our uncertainties to better than one significant figure, as we've talked about before. What we'd need to do is round to this one significant figure there, but we also always need to round up so we don't underestimate our uncertainty. So what that gives us in the end is the uncertainty on the average value of the voltage, 0.02. And you'll notice here that the uncertainty on our average value, when we looked at 5 readings, was 0.02, whereas on an individual reading or individual measurement, it would be 0.03. So the fact that we took more measurements has given us more certainty on what that average value is. And I'm just going to over here give our final answer. So our voltage is the average value that we got plus or minus the uncertainty 0.02, and that would be our final answer. And the only other thing I wanted to point out here was that this range that we've got here, 1.56 plus or minus 0.02, suggests that the true, or that average value, lies between 1.54 and 1.58. Now we do have individual readings which are outside of that range, but that's just because of random errors, and by taking lots of data we can pinpoint that average value with a bit more certainty.